Okay, as a courtesy, I'd like everybody to ask themselves to mute themselves. Okay, thank you. All right, yeah, welcome everybody. My name is Hazik. I'm a reservoir engineer at ExxonMobil, and I'll be your moderator for today. So today we have an exciting talk titled Machine Learning Reimagined, Reservoir Characterization, with examples of case studies from the field by Mr. Balaji Chennakrishnan. So I'd like to thank everybody for taking some time out of their busy schedules for this talk. So currently we have 26 participants. I can see more are streaming in as time passes by. So before we begin the talk, just a few items that we'd like to go through. So thank you for tuning in. You can follow SPE Kuala Lumpur section on LinkedIn, and you can check out our YouTube by scanning the QR codes over here. All of the content that we have for this Members in Transition Distinguished Lecture sessions are all uploaded onto YouTube, as well as other content from our activities. Just a few housekeeping rules. So the lecture will be between 50 minutes to 1 hour. We have a 20 minutes Q&A session, as well as 10 minutes for our Kahoot quiz. So as a incentive for you to pay attention and to stay to the end, there is a prize that will be that is sponsored by SPE Kuala Lumpur section for winning the first place in the Kahoot quiz. So do tune in and try your best. Please mute your microphone if during the talk. The session is being recorded, so if you're not comfortable with that, you can always watch the recording later on. If you do have any questions, you can please type them in the chat box or raise the hand feature on the panel. And you can also ask the questions during the Q&A session at the end. And do stay until the end of the talk to claim the prize if you're in the first place, or email us at the email below. All right, just a quick one on SPE professional membership. I think we've gone through this every single week, so we're going to keep it a little bit short in the interest of time. Basically, the SPE professional membership has a lot of benefits, and the costs are reduced in this pandemic time. So do check out spe.org/en/join to find out more about the membership. Okay, now on to the talk. So again, the title for today is Machine Learning Reimagined, Reservoir Characterization. So the talk will focus on the use of machine learning approaches in enhancing reservoir characterization efforts based on use cases applied in real fields as a part of projects executed. So the talk will cover 3 case studies, the first of which is a case study of using unsupervised classification techniques such as self-organizing maps and generative topographic maps to bring out seismic facies characterization. A case study on automated well correlation using convolutional and autoencoders and clustering methods, and as well as a case study on automated reservoir rock typing using the dbScan and T-SNE algorithms. These case studies have clearly demonstrated on how machine learning-driven approaches can enhance conventional reservoir characterization efforts and also adds tangible business value. So a little bit about our speaker for today. Balaji Chennakrishnan is the founder and CEO of Telesto Energy, a Singapore enterprise at the forefront of building machine learning and artificial intelligence-driven solutions for upstream oil and gas. Prior to Telesto, he has worked for Petronas, Kuwait Oil Company, Jubilant Energy, Reliance Industries, and Geoservices across Asia Pacific in various capacities. He's an expert geologist with over 24 years of industry experience, and his area of expertise includes reservoir geology, integrated reservoir studies, reservoir modeling, operations and development geology, as well as asset management. Balaji holds dual master's degrees in geology from University of Madras, India, and petroleum engineering from University of New South Wales, Sydney, Australia, and an AAPG reservoir characterization certificate course by Roger Slatt from University of Tulsa, Oklahoma, USA. Balaji is passionate about developing machine learning and AI-driven solutions to upstream oil and gas business and has led Telesto Energy in building enterprise-scale AI solutions. Stardust Insights from Austria has named Telesto Energy as one of the top 5 predictive analytics startups globally for oil and gas. All right, and without further ado, I think, Balaji, I'll stop sharing my screen so you can begin your talk.
Sure, yeah. Okay, good afternoon, everyone. Please let me know if you can see my screen.
Yes, we can see your screen.
Okay,
Yes.
yeah, thank you. Yeah. Am I audible? My voice is clear?
Yes, loud and clear.
Okay, thank you very much. Okay, first of all, I would like to thank SPE KL for giving this opportunity to present, and I think I really appreciate the effort SPE KL is doing in this Members in Transition series. And thanks, Afik, for the excellent introduction, and I really appreciate, and Rosemawati for the coordination and making this talk possible. Okay. Today I'm going to talk about how machine learning approaches reimagined reservoir characterization. And these are the case studies that we have implemented in some of the projects that Telesto Energy has done for our clients. And also, I'm going to show the data on some of the open source fields so that this data can be shared with the members later. So before I start my talk, I think an acknowledgement is due for Telesto for providing the permission to present this work. I'd also like to thank and recognize the immense contribution from the team members, Amit Kumar, and Sarah, Nitish, and Shashipal, all from Telesto Energy, for making these ideas from a concept to reality to implementation. And also, I would like to thank Rajeshwaran and Aditya, again from Telesto Energy, for their support and supervision. So also thank our partners and clients who has supported us and provided us with the opportunity to implement these techniques. So today's talk is going to be on 3 case studies. What we are trying to show here is how we have successfully applied machine learning concepts in real field examples, and these are a complement to conventional approaches that are being practiced in day-to-day activities that a geoscientist perform. The talk will cover 3 areas. One is well log correlation, how using machine learning algorithms we can automate the well log correlation in some cases. The next one is reservoir rock typing. Reservoir rock typing is something the geomodelers and petrophysicists and reservoir engineers do in effect to do integrated reservoir studies and building static and dynamic models. And we have used a case study on how unsupervised clustering techniques can be used to automate the rock typing. And the third one is on seismic phases classification using advanced machine learning techniques. So the first case study I'm going to talk about is automated well correlation using machine learning and facial recognition technique. When I say facial recognition techniques, these are techniques that are used widely. In this case, we have used CNN. This is a image pattern recognition approach. So this case study is what we call automated top picking. The objective of this case study was to pick the well tops automatically so that we can reduce the interpretation time and repetitive work. Just imagine doing the correlation again and again for a field having 50 wells, 100 wells, 150 wells. I mean, this is a time-consuming work. And once the framework is set, and if we can automate this well top picking, this will reduce a lot of time. And here we have chosen a Kansas Basin in USA, where we have implemented this on more than 50 wells. This is one of the case study. The other 2 case studies that we done on this is actually on the projects that we did to our client. So how we did that? We used a convolutional autoencoders and classifiers to recognize the pattern, and we use supervised and unsupervised clustering methods. So how does this benefit? So like I said earlier, it's a quick update on correlation. Say that you have 2 or 3 wells data that's coming in. You don't have to go through the whole correlation again. You can simply automate and do a quick QC. and it doesn't matter how many wells you have, whether few wells or more than 50 or 100 wells can be done very quickly, and it's purely data driven, and it follows the existing patterns, and it really helps in efficient decision making. So just if you can look at this screen, what you see is a well correlation section. In a well correlation section, you will see different wells and with the logs displayed. In this case, we have used gamma ray, neutron intensity, and you can see the peaks. You can see the different colored lines going from left to right of the cross section. These are essentially different well tops picked based on some log signature. The log signatures respond to various things like gamma ray and density neutron responds to lithology variation, resistivity responds to the fluid typing. This is very well known. This is very fundamental to the well correlation techniques that are being followed. And you can also notice there is a pattern. The pattern, excuse me, is very similar, and it extends across the wells, across the field. There could be some minor variation, but if you see, the patterns are generally consistent. So this is these patterns are what we are looking at, and this technique identify similar patterns and compare with the existing logs, and using convolutional autoencoder and feature vector cost maps, we can pick the stops automatically in the new wells. Sorry. How does this work? First, it's 3 stages. One is data preparation and model training, and doing the actual auto well correlation. Data preparation is actually very conventional, very typical of what is being done on a day-to-day basis. You prepare the loss files and training the model. In training the model, what we did in this case is like we have taken some type logs. Type logs are wells wherein the log signature are very typical for a particular reservoir or a particular zone, and so we have used those type logs for creating a training data, and using that training data, we train the model. So once we train the model, and we have a data structure essentially from where it can the data is stored and read from, and the well upon applying this machine learning algorithms, the automated well log correlation is performed and plotted. So how does this work? Convolutional autoencoders were used to convert the multi-dimensional data. In this picture, you can see the well logs represented on the left-hand side and bottom. These are from 2 different wells, the gamma rays. And what you can see here is like there are different peaks of different magnitude. These are read using convolutional autoencoder. What does that mean? Is like it is like a CNN. It's a neural network. This is typically used in image recognition. Like when you, the simple examples people use is like identify cats, train the images, and read thousands of images of cats with different background. And when you show for the program your new cat, and it automatically identifies that this belongs to a cat. This is a very similar kind of approach that we have used. So not only it detects the image, it also does the encoding of the image. So the label using this the similar peaks of 2 different wells or more than 2 wells from one curve or more than one curve can be identified and mapped. And this is how it happens. So we choose an interval of a reservoir, let us say the reservoir interval of 500 meters. We pick the logs and extract the window, and it compute feature vectors. Feature vectors are essentially the points or the image, depending on the intensity that are plotted, and The third step, the key points are identified based on the difference of Gaussian, and these are like plotted on a feature vector map. Now what you see at the bottom is it has identified multiple peaks and compared that with well-logged peaks from a different well. And you can also see a red curve indicating there is a reasonably good correlation and the data fitting and matching is fine. In this case study, we have picked up oil and gas field in Kansas, USA, where we chose more than 50 wells from the following counties: Thomas, Scott, Logan, Barton, Stafford, and Vicia. And this is the base map that is showing the wells. There are a lot of wells. We have picked only from a few counties. This is the stratigraphy. Essentially, we chose this for one reason. This has different lithologies like coal, your shales, limestone, siltstone. This is the type log. What you see in the type log is identification of different correlation units or lithologies. What you can see on your right hand side is the peaks for coal, limestone, shale, and silty sandstones and stales. You can see a number of tops have been picked. The interval is from 900 to 2,300 feet. And we have also used coal markers as a reference for subdivision of different units. So here we have applied auto well correlation and to see the depth matching as well as horizontal connective identification between two wells. So this picture will tell you like how the peaks are matched between two different well log curves from different wells. And this is the extrapolation of this technique over a number of wells, and we have picked around like 22 units. And the overall, the results were good. I would say around 90 to 95%, but for some wells, it's a bit difficult. So when one example where we notice what if the GR is too blocky, it's like then the pattern recognition sometimes doesn't work. But otherwise, overall, the results were like very satisfactory. The comparison between a conventional well tops picked, what you see on the two wells on the right hand side, and a similar comparison with well tops picked using automated well correlation. So what you can see is in the conventional approach, there were 10 tops picked. In the automated approach, those 10 tops were picked. Besides those 10 tops, we also picked more than 11 additional well tops. And this is automatic. There's no manual intervention here. And also, we could see a very good match in terms of the well tops picked using this machine learning algorithm, as well as the well tops picked manually. So, okay, this I'd like to highlight some of the key points of this approach. The variety of machine learning techniques are available for standardizing and scaling of data. So the approach using convolutional auto encoders to identify the matching depth points, it produces good results, and it can be adapted easily and very scalable, especially if it is within the same field and same basin. So we don't need much of training. But if you are going to use it in different fields, some kind of like training is a prerequisite, and log data processing is also a prerequisite. So we have some other plans using different algorithms in future to improve the accuracy levels. This is the first one. The next one is a case study on how we can automate reservoir typing using unsupervised clustering techniques. So this case study, what we call automated reservoir rock typing. The objective is to automate the rock typing approach using machine learning. Here we have used all the available logs and code data that could be associated with the lithofaces. Rock typing is essentially a lithofaces, and lithofaces you extrapolate to the rock properties. So this case study has been performed in a gas field in Middle East. We have used more than 45 wells. This field has excellent logs and also cores, and that was one of the reasons why we have implemented here, and we could see the results were like quite good. Here we have used two algorithms, with density-based scanning and the TSNE, and unsupervised clustering methods. So what are the business benefits? It captures all lithofaces. In conventional approach, if you see, when we do lithofaces, we have to lump lithofaces. The reason is we have limitations in terms of how many lithofaces we can take into the modeling approach. Here you can capture all the lithofaces, and it's very quick in building this framework. So here I want to give you a comparison of this workflow, how it is done conventionally and how it is done in the approach that we have chosen. So the first three steps are like a common, which is gather your data and QC the data. These data could include your logs, your cores, your routine core analysis data and SQL data, and log preparation, standardization, normalization. This is very critical. So, and the third one is the electrophases identification through cluster analysis. Here, when you go to the conventional approach, you can only represent the data in two-dimensional spaces generally. And the clustering is generally using k-mean. The issue with k-mean is you need to define how many classes that you need to have. So it's a more deterministic approach. It does not allow the natural clustering to form beyond a certain level. And where in the machine learning model that we have used, here we can represent the data in n-dimensional space. When I say n-dimensional space, means like you can take more than 2, 3, 4, 5 logs as inputs and still can represent them. Then once we represent that, we use TSNE to reduce the dimension, because you need to bring it to a lower dimension to plot and analyze. So then once that is done, we use the clustering using dbScan. And once the clustering is done, we define the boundaries. Once the boundaries are done, then we again link it. Let us say this is like a correlation with the core data, and then define the reservoir rock types as like whether they are good, moderate, poor, or non-reservoir. So, and these are some of the algorithms that are used for clustering. Here we have used TSNE. TSNE is a dimensionality reduction technique where you can bring in high dimensional data for visualization into a low dimensional space of 2 to 3 dimensions. So dbScan is a density-based spatial clustering of application with the noise, very robust in detecting outliers. It does not require to be specified on how many clusters you want. But this is unlike of k-means. K-means is a traditional approach, but you need to define how many clusters you want to have. Here, what you can see is like we have taken 3 logs, gamma ray, density, and neutron. And these are plotted in a 3-dimensional space here. For example, you can have as many logs as you want. So all this input data are formed into a cluster, and you can clearly see the data clusters colored in different colors. So now once that clustering is done using unsupervised method, an iteration between TSNE and DBSCAN, so the number of distinct classes are identified, and we have also applied a k-mean to see how the k-mean clustering approach responds. What you can see on the right hand side, the results from both k-mean and DBSCAN and TSNE. What is very obvious is DBSCAN plus TSNE is able to bring out the different faces very clearly, whereas in k-means the distinction is not very obvious. So once we have done the clustering using this approach, we need to define boundaries. In this case, we have two different deposition environment. One was braided delta, the other was alluvial fan. So we could derive 6 such classes for braided delta deposition environment, and 3 classes for the alluvial fan. So this is the histogram and the distribution of classes, and also the boundaries that all of that you can see on the right hand side. So now comes the calibration part. So what we have done is this clustering and classification was done from the logs. So we have used the cores, and from the cores we plotted the poroperm data, and that data we clustered again. And what we could see is a good match between the classification that was done from cores and routine core analysis data. You can very clearly see the similar distribution of lithophases classes can be seen from the cores as well as from the logs, and this has been also compared with the core data, and the results are reasonably matching. So now we have to plot this the phases. What you see here is like on the right hand side is the rock typing that was done using a conventional approach, and how does that compare with the approach that we have adopted. Please note that the colors are not exactly same. I will explain, but if you can see my arrow like this, what you see on the right hand side is a conventional lithophases done using traditional approach, and this one is the for the same deposition environment, the lithophases, automated lithophases done using like machine learning techniques. What you can see is here like this one is a massive sandstone, and that is clearly represented here, and this one is poor phases, moderate phases rather. Here you can see a number of lithophases classes within that, and here also the representation is more, and especially when we see the number of lithophases classes that we could derive on the braided delta, this is much more. So concluding this, this is a novel approach. This is a very quick and scalable framework when it comes to 3D static modeling, and we can get much better insights by using multi-dimensional data. Traditionally, we use 1 or 2 logs. Here you can bring in as many logs as possible and plot it in n-dimensional space, and we can reduce the dimensionality so that we were able to do the clustering and analyze them. So this is the conclusion of this case study, and these are some of the publications that we have already done on this case study. The third one is about seismic phases classification using advanced machine learning algorithms. So here we have used SOM and GTM, What it does is it does a fast and effective FACIES classification based on number of relevant seismic attributes. So this is validated using well data and identifying and mapping of the sweet spot. So why we have to do this? Now typically when you are doing attribute analysis, trying to identify seismic phases, there are a number of attributes one need to analyze, and this is a huge volumes of data and time consuming. By automating this one, you will be able to bring in the genetic relationship that is displayed by through number of these attributes, and it is a fast and quick approach. So what is the solution? The solution, SOM, is an unsupervised classification technique. So it generates natural clusters. That means when you input a number of data sets or attributes, all the clusters that are related are naturally brought out. So you can automatically identify the spaces. So how it benefits, it actually expedite the interpretation time. The interpretation is faster, and also it brings out much more clarity in the data when compared to when we do it manually, and it's quite beneficial at the exploration stage of the field where the data availability is minimal. Here is a comparison on how it is done, what is conventionally, and what are the approaches that is available using machine learning. In conventional analytics, we use cross-plotting, slicing, 3D visualization, and extract the geobody. In machine learning, there are two approaches. Here we are going to talk about only the unsupervised learning approaches. Generally, the self-organizing.
Hello, Assalamualaikum. Pedas, boleh dengar kan? Can you hear me?
Hello. Hello.
Sorry, just you can proceed, Balaji.
Okay, yeah, sorry. Okay, so in this approach, we used self-organizing maps and generative topographic maps. There are some supervised learning techniques. This we have not used in this case. So how does this work? So in unsupervised classification, like I mentioned earlier, the key is this is very useful in exploration phase of the field. So we bring in the relevant seismic amplitude data and the attributes. It's very key. The selection of the attributes is very key, because if you are going to detect seismic phases, you need to bring in attributes that are going to give you the result. At the same time, not bring in very similar attributes so that you don't get much benefit, except that you will be wasting a lot of computing time. Then with that attributes, you apply unsupervised machine learning algorithms such as k-mean clustering, SOM, and GTM. Then using this automatic pattern recognition and classification, natural clusters are formed. Then the phases are identified. Then it's again the interpreter's insight and their experience. So that's quite useful here. Whereas the supervised approach is generally used, suggested to be used in the development phase of the field life cycle. So here we have used two approaches, what we call SOM and GTM. SOM is self-organizing map. GTM is generative topographic mapping. Both are data-driven. Data-driven. There is no bias, no a priori information. So that means without any input guidance or anything, this clusters or classification happens naturally based on the data that you are providing. It's a very robust technique. And what we do in SOM is, again, like what I mentioned earlier, you can bring in as many data sets as possible. That means like n-dimensional data is possible. And then we project it into a lower dimensional latent space. So this is critical for doing the analysis. But it does preserve the geometrical or the genetical relationship between the data points. Similarly, GTM is also a robust unsupervised classification technique. This addresses some of the inadequacies in SOM, and this is based on probabilistic representation of the data vectors in the latent space. So this is how it works. Now, what you see on the top left is a representation of different seismic attributes on a like three-dimensional representation. So like you can bring in as many number of attributes here. So what there you can see two types of like dots. One is dots blue block dots which are filled in, and the other one is like the dots with only the outline is there, like I would say empty and full, kind of like dots. The blue black dots are the prototype vectors. The input data is from various attributes. These prototype vectors represent the input data from various attributes in 3 dimensions. And these prototype vectors, let us say here we have used 5 different attributes, and this input data represent all this on all. For each prototype vector represent all the input attributes data at that three-dimensional space, and this is projected. What you can see on the top right, this is projected onto a two-dimensional grid. It's 11 by 7, and this is customizable depending on the amount and volume of data that you are going to use. So this, just remember, this is higher dimensional data projected into a two-dimensional data latent space. However, it carries all the characteristics of all the attributes and preserve the geometrical relationship. Then once it is projected onto a two-dimensional SOM grid space and using SOM and GTM, and this is finally projected onto the grid by forming different clusters. So these natural clusters that are coming out from this approach are assigned. That is what you can see on the bottom right, assigning colors to different clusters. So these clusters are extracted and gradational HSV color coding is done of the trained prototype vectors for better visualization. So what you can see here is seismic attributes of different types, and those prototype vectors are represented or projected onto a 2D latent space, and applying SOM GTM techniques, the natural clusters are formed, and the natural clusters are further enhanced using the different colors technique. Now, this is how the workflow is. So the amplitude data and the data conditioning, and then you generate the attributes, then you run SOM and GTM algorithms, and the projection on axis volumes. So then there is a automatic pattern classification, natural clustering happens. Then again, the interpreter's experience and expertise is very crucial. So then the seismic facies classification is done, and this is again validated in the well data. So in this case, we have used a case study from offshore Nova Scotia. So there are 3 major reservoirs: Logan Canyon, Mississauga, and Abenaki limestone. So in this case study, we're going to discuss the results that we obtained from Logan Canyon and Mississauga formations. So this is the data conditioning part. The seismic data is conditioned to provide cleaner data. The workflow is given here. The key point that I want to highlight here is the choice of attributes. Here we have chosen coherent energy, textural and GLCM attributes, spectral magnitude, sweetness, relative acoustic impedance, and coherency. So idea behind choosing these attributes is to represent the reservoir continuity, the boundary conditions of the reservoir defined very clearly, the hydrocarbon presence of the reservoirs. These are like the attributes chosen very carefully to represent the various aspects of reservoir characterization that is normally done in seismic reservoir characterization, so that when you apply this SOM and GTM techniques, you get the full benefit of the phase, not only the phases classification, you bring out the overall reservoir geometry with some clarity, as well as the hydrocarbon bearing properties of the phases. Plus, you also capture, you also reduce the errors by using some other attributes which are not required. So the second point is all these attributes chosen represent a particular quality or character of the reservoir. We have been very careful in not repeating the attributes that produce the same kind of output because these are all like seismic cube volumes. The computing requirement is quite heavy. So so one has to be very careful and very clear on what they are trying to achieve here. So this is the attributes, what you can see on the coherence as well as spectral magnitude attributes at the Logan Canyon shallower level. You could see channel geometry, but not very clearly. So this is essentially a test showing like your convergence of the beta. And here we could see it stabilizing around 50 iterations. So once we apply this SOM and GTM classification results at the shallower level, so what you can see both on the left and right hand side, both these maps have clearly brought out the channel geometry and the other associated crevasses plane, floodplains, point bars, etc. And you can also see the natural clusters that were formed in both GTM and SOM are well separated. That means these are all like bringing out the geometrical relationship of various phases bodies very clearly. So, in comparing both these maps, what we could figure out is GTM was able to bring out the heterogeneities a lot better compared to SOM. So this is another level in the Logan Canyon, deeper level. What you can also notice here is the channel is brought out very clearly, and we observed a gap there in between. So we wanted to cross-check with why there is a gap that is existing. We can see in this area. So why there is a gap existing? So we thought this is a fault zone. So we again superimposed a curvature attribute to see whether this gap is a faulted zone. And what you could see very clearly is like this channel was cut by the fault. And this is at the Mississauga level. Again, what we can see is here the data vector. What is the possibility of this data vector being an edge member? That means like this could be a different phases. So that is what we are trying to plot, and what we could see is finger-shaped sand bodies that were like noticed, and this actually was also tested in. We tested this data in one of the wells where this had shown some hydrocarbons, but the well was slightly off from the main SAM body that we can see here. And one more thing I want to highlight here is this is plotted against the mean. So what you see here is actually the distance of this n member compared to the mean of all prototype vector. So, in concluding this topic, some of the crucial things are like the seismic data conditioning is very, very crucial so that we adopt undesired coherent noise. And both these techniques help in identifying the seismic phases. And one important thing is the clusters are formed naturally and they are very distinct. And they also bring out the geometrical relationship within the phases. GTM is better in terms of addressing the heterogeneities. So this is what we observed is an excellent pattern recognition tool for seismic phases classification. That I conclude my presentation. I'm ready to take any questions, and if somebody is interested, I can just quickly run through the solution architecture, but this is outside the scope of this presentation. Essentially, the data source as a cloud or local server, and the integration, how we bring the data using the ETL tools like Talent, Azure, Informatica, and then we apply these machine learning models, and this output can be taken into any of the existing software and applied. So thank you very much for your patience, and I'm open to questions and any discussion.
All right, thank you, Balaji. I think we have a question already. I see, Duncan, you have your hand raised. Go ahead.
That's correct, yes. Thank you very much indeed for an excellent talk. It was very interesting indeed. I've got to say, you made a pretty good case, I think, for machine learning and clustering for the seismic facies and also for the facies classification. I've got to say, actually, quite a few years ago, I used to do quite a bit of hydraulic units work, and I was doing something very similar, but very much more on a conventional basis. I could have done with some machine learning 20 years ago to speed things up. But I do have a little bit of a concern about the very first case study, which is well correlation.
Mm-hmm.
I can see how, yes, if you're maybe in a sheet-like sort of environment where you're looking at perhaps marine facies or marine types of depositional environments, that maybe if you've got rather sheet-like geometries, yes, that's something automatic like that would probably give you maybe a first pass. But I'm a little bit concerned about not having too much or not having enough operator input here, because I did a lot of work actually correlating between wells in a tidal sort of channelized type of setting, where quite often a completely different channel at about the same level can look almost exactly the same as another channel in another well, but you can't correlate them because they're not connected. So I'm a little bit concerned about you maybe automating it too much. And okay. The other thing about this is that you're dealing with very much a lithostratigraphic method here. So do you have any suggestions for getting around that, or trying to mitigate some of those concerns?
Wow, excellent question, Duncan. I think this is something I wanted to highlight during the talk. The area we have chosen is pretty simple, it's not a complex geology, like you mentioned, like a sheet-like structure. The reason we chose to do that was our primary objective was to see whether these techniques can be really effective. Like I said, these techniques work like facial recognition techniques. That means they see a pattern and they see whether that pattern is repeated, and then they just go. and how the more training you give to the model, they get better at it, but they cannot actually work so well in all types of geology, because like what he said, in a lithostratigraphic setup, it's okay, but when you look at a chronostratigraphic type of like a distribution, so these are challenges. So what we are actually working on is, if you have noticed, we have used unsupervised approach. So unsupervised approach means like we let the data speak. So, but that's not good in all situations. So that is why we are working on a combination of supervised and unsupervised approaches, wherein, let's say, like in a deep water setting, we have, in one of the case studies, we are actually working on a deep water setting. And we have already predefined well tops, and we use that as an input and use the model to train. And even that is not very effective. So we need to go for a reinforcement kind of learning. That means like you see the result, and this result is very specific. Like, if you give me 1 minute, I'll just give one example. Like if you see a turbidite channel, where the log signature on the axis of the channel, whereas when you go to the edge of the channel, so it's totally different, but they represent the same reservoir body. So how does your machine learning methods work in cases like this? So this is where we are trying to use reinforcement kind of techniques to see whether this is effective. So of course, this works in some cases very easily. Like your apprehension is very valid, and this cannot be universally applied, and you have to go on a case-by-case basis, and preferably with some expert eye overseeing what you are doing.
That's excellent. Thank you very much indeed. That's a good talk again. Thank you.
Thank you.
Yeah, Balaji, I have a question for you as well. So I'm not, I don't have a background in geology, so I just wanted to know sort of where does the machine learning reservoir characterization, we use that to develop some kind of models or geo models, and let's say that is being run, in a reservoir simulation, or where we do have some kind of history matching and things like that. If our history matching shows that the reservoir characterization needs some kind of tuning, or there's some changes to be made, I was just wondering, how does that play into the machine learning aspect of it? Like, do you go back, take those results, and retune the models or the methods that you use to train the reservoir characterization, or not?
Okay. So I will answer this question slightly different, not very specific to the question you asked. See, why we do this, apply these techniques. So we apply these techniques to get a deeper insight into the data that we are dealing with, and also minimize the uncertainties in the data that we are dealing with. So these are all standard statistical approaches. This can be used in any industry, so not necessarily in oil and gas, or not necessarily particular to simulation. So currently what's happening in the industry is people are working on specific areas. Like you are talking about going back on the simulation. That means simulation is output of an integrated study. So that means there is so much of data from so many disciplines, and so much of work is being done, and you see the results. And you cannot use machine learning to reverse the wheel. So what machine learning can do in the situation is, you need to see each and every process and where your machine learning can be applied. Like in our case, like whether you do the rock typing or whether you do the well correlation, these are all inputs to building a static model. Whether you can build a static model using machine learning, I would say the answer is no, at least for now. So what you can do using machine learning is you break down the whole process into small modules, if you may, and apply your machine learning techniques so that you improve the final results and accuracy. Have I answered your question correctly?
Yeah, I think I understand a lot better. Yeah, thank you. All right, see if there's any questions in the chat. Yeah, if you have any questions, please place them in the chat box or you can unmute yourself. So we have a bit of time. We have about 30 minutes before our session ends. Balaji, maybe you'd like to go through the architecture that you showed earlier while we wait for some questions.
Sure. So in our case, what we did, the data source, data integration, data repository, that's essentially your database, and your model building and deploying, and how you want to see the results. So these are all essentially the different components of this architecture. The data source can be anywhere. Let us say data lakes means like you have your own what do you call, like data storage, which they call data, and the sensors and cloud are different areas from where you get the data. Here sensors doesn't make any sense because there is no sensor data that's coming in. The data can be in the cloud, whether it can be in your own company cloud or it can be in Azure or Amazon Web Service or something like that, or it can be in your own local server. So it doesn't matter where the data is. So what we do is like we use tools which call like ETL tools. What they do is like they extract the data from wherever it is and load it, and we have the tools that transform the data so that the input data that you are having for your model is prepared and is in a format that is easy to run your model. So these are some of the tools that we have used: Talent, Informatica, and Azure, HT Insight, and these are brought in SQL or Cosmos DB. There are a number of databases that you can use. So the models is very key. So how you build your models, there is a number of ways you can do. Machine learning models generally, like they all come under the deep learning architecture. So one has to use tools like TensorFlow, Keras, and Python, PyTorch, and the Flask and Django are like what do you call, like the data cases, and we also build a user interface, which is like API, where you can actually vary the processing parameters and see whether the data output that is coming is as per your expectation. So the output can be hosted anywhere, like you can host it on a web, you can host it on Azure, you can host it on your server. And again, the whole processes can be taken as an input to your existing software, or the dashboards. You can have your own visualization tools, or you can have visualization tools like Power BI and Tableau. But one must understand this, like the available visualization tools currently, the commercially available visualization tools for oil and gas applications are very, very few. If you go with the standard tools such as Power BI and Tableau, you are very much limited with what you can do and what you cannot do, because these dashboards are not built for typical oil and gas applications. These are more like for financial and other kind of industry applications. So it's good if you can build your own visualization to some extent, because viewing the seismic data and seismic attributes, I don't think you can do it using Power BI or Tableau. You need to have something on your own, or there are some tools available in the market which you can use, or you can take it as an output like a segue, and you can reload it into Petrel or other softwares and see how the results are and how they compare. This is the typical solution architecture that we used. So again, I think maybe the topic is not that interesting or really good. We can go for the quiz, and if somebody has some questions after the quiz also, we can entertain if there's something.
I saw this. There's one question from Nur Aslan.
Yes, there's one question by Nur Aslan. Are there any case studies done in Malaysia with these techniques?
We would love to do it. These case studies are mainly done in Middle East. So far, no case studies done in Malaysia. We hope we will be getting an opportunity to do it very soon.
All right. All right. I think we can probably move on to the quiz. So, Balaji, if you could stop sharing.
Sure.
Oh, that's my bad. All right. So yeah, before we move on to the quiz, I'd like everybody to take like 1 minute to go over our feedback form. I pasted the link in the chat as well for those of you who are not able to scan. So I'm going to give 1 minute for everyone to be able to take this information down. After that, we'll move on to the photo session as well as the Kahoot quiz. All right, it's already 1:07. So so I'd encourage everyone to switch on their photo for a quick group photo session. I'll stop sharing so you can go to together mode. All right, we see we have 9 people with their cameras on. Anybody else? Okay, that's 10. Okay, I guess everybody's shy today. All right, I'll just be taking the photo then. So let me do a countdown. Okay, in 3, 2, 1. All right. Okay, let's do one more. In 3, 2, 1. All right, thanks everyone. All right, we can probably move on to the quiz session now. So let me just launch that up. Okay, can everybody hear my volume all right? The audio?
Yep.
Yes.
Yep. Loud and clear.
Awesome, awesome. Okay, so, all right, we see some people coming in. For those who are not familiar with how to play Kahoot, you can follow the instructions on the screen here. Go to www.kahoot.it and enter the game and enter this game pin. You'll be redirected to a page where you can enter your name and join the quiz. So remember that we have a cash prize for the first place winner of the Kahoot. It will be a 50 ringgit e-voucher sponsored by SPE Kuala Lumpur section. So you never know, you have a shot. Hey, we have 20 people in the house. Let's give it maybe one more minute. Oh, Balaji, are you joining the game as well?
I'm not going to play, I'm just going to be there.
You'll beat everyone here.
No, don't worry, I will not answer. Just wanted to join the fun.
Awesome, awesome. Right, we have 23 people in. Maybe I'll do a countdown. So in 10 seconds, we'll start. So in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, let's begin. So machine learning reimagined reservoir characterization. Okay, and we start off with a very difficult one. Python is a big snake, son of Satan, a non-venomous snake, or an open source programming language. All right, pretty much everybody got that right. Awesome. Let's see who's in the lead. So currently SJP for me in the lead. Awesome. Let's go to the next question. All right, a random forest is a supervised learning algorithm, a type of cake, a forest of trees, or a method to group objects. All right, that's correct. Most of you got that right. It is a supervised learning algorithm. Okay, let's see who's in the lead now. All right, Agi takes first place. Okay, CNN is a television channel known for fake news, China News Network, a convolutional neural network, or all of the options here. Oh, this might be a trick question. I wouldn't know. All right, everybody got that right. It is a convolutional neural network. All right, Agi retains his first place, and it seems like MCO has the highest answer streak. Okay, next question. What happens in machine learning? So, does the computer do some coding, or is it use of computer algorithms to analyze data, humans teaching machines to solve complex problems, or is it none of the options here? All right, about half of you got that right, or no, that's about 60%. Use of computer algorithms to analyze data. Awesome. Still Agi in first place. So let's see if anyone can topple Agi in the first place. Okay, next question. Intelligence displayed by humans and other animals is termed. Is it cognition? Is it natural intelligence? Is it natural ability? Or is it all of the options here? All right, the answer is natural intelligence. So seems about 40% got that right. Wow, still Agi in first place. Awesome. And W with the highest answer streak of 5. Looks like he's catching up slowly. All right, the battle goes on. Which of the following is not a machine learning algorithm? Is it unsupervised learning, supervised learning, Python, or reinforcement learning? Awesome. So most of everyone got that correct. And Agi's still in first place. Let's see who can take him down. Okay, this is a true or false question. Images for cat recognition is an example of structured data because it is represented as a structured array in a computer. True or false? All right. Answer is false. Let's see. Okay, very few got that right. Okay, and AZ in the lead. Okay, next question. Which of the following analytics is least complex? Is it descriptive, prescriptive, predictive, or prospective? Okay, answer is descriptive. All right, AZ still in the lead. So CNN is mostly used when there is structured data, unstructured data, both of the blue and red options, or none of the options here. All right, answer is unstructured data. About half of us got that right. Awesome. AZ still in the lead. Okay. So RNN stands for receptive neural network, recording neural network, redistributed neural network, or recurrent neural network. Awesome. The answer is recurrent neural network. Just a bit less than half. Okay, AZ still holds on to his lead. Question 11. In which of the following can we use machine learning to solve geoscience problems? Automated fault detection, seismic fault characterization, both blue and red options, or none of the options here. Okay, and the answer is both blue and red options. Oh, AZ just lost his lead. Amy in the lead now. Okay, what does the analogy AI is the new electricity refer to? So is it like electricity, AI powers our personal devices? AI delivers a new wave of electricity through the smart grid? AI allows electricity-powered computers to do things not possible before? Or just like electricity 100 years ago, AI is transforming multiple industries? All right, the answer is just like the electricity 100 years ago. So I guess the second industrial revolution, AI is indeed transforming multiple industries with IR 4.0. Okay, AZ back in the lead. Okay, for our last question, it's a true or false. So let's see who can get first place. So a data set with statistics on different cities' population, GDP per capita, etc. is considered unstructured because the data has multiple sources, as in the data comes from multiple different sources. Is this true or false? Okay, answer is false. Okay, so now let's go for the big reveal. In third place, we have Shar. In second, we have Amy. So that can only mean in first place, we have AZ. Okay, congratulations, AZ. And shout out to our runners-up, iTry and Agi as well. Okay, so for AZ, if you could stay just a little bit after the session ends, and you can claim your prize. Okay. So once again, everybody, thank you for attending our session and taking some time off of your lunch break. We really appreciate it. Thank you to Mr. Balaji for the excellent presentation. So Balaji, if you could let everybody know how they could reach out to you, maybe if they have any questions or they would like to find out more. Oh, sorry, Balaji, you're muted. Let me...
Okay, okay, sure. Sorry, Hazik. They can reach out to me. You can share my email to them, or I can type here in the chat box. It's simple, balaji@telestoenergy.com. If they want, if someone is interested to know more, we are open. Like we want to spread this knowledge to the industry, and I really appreciate the opportunity, Hazik, and Rose.
Okay, thank you so much. All right, so that concludes our session, everybody. Once again, thank you. Thank you, Mr. Balaji. Thank you for everybody attending this talk. So have a great day and stay safe, everyone.
Okay, yeah. Thank you. Thank you very much.
Thank you so much.
All right. I guess I just want to share one last thing, which is the next week's session. Let me see if I can share that. Yeah, so for the next week, we have a session with Amy Yusnita, a walkthrough of Malaysian PSCs. So that will take place same time next week on 25th August, Wednesday. You can scan to join, and we'll be sharing the link as well in the email to our SPE section members as well as on our LinkedIn. Okay, so for AZ, winner of the Kahoot just now, if you could just stay back just a few minutes.
Thank you very much.
Okay, thank you.
Yeah, bye.
Bye-bye. Stay safe.
Yeah, you too.
Hi. I think there's no need for to stay back for too long because I'm easy.
Oh, congrats, Isha.